Thank you for the introduction, and thank you all for coming to this session. My name is Chiaki Shio, and I'm present my work about delimited control operators. So I would like to begin with a question. So how to understand the control abstraction from the type level perspective? So when you hear control abstraction, maybe you think about monads or effect handlers or delimited controls. And ultimately, I would like to understand all these things in a type level. But as a first step, I would like to understand I would like to understand the delimited control from the type level perspective. So this is what our paper is about. So as a quick review, what is a delimited control operator? So these things can control the flow of the program, and basically they provide a set of two operators. The one is capturer, and the other is the delimiter. So for example, shift and reset is one of the most famous delimited control operators, and S denotes this S here denotes shift, the capturer, and the angle bracket denotes reset. So you can use shift and reset like in this example below. So first, when we are trying to evaluate this equation, shift is going to capture the context up to the surrounding reset operator. And then shift is going to reify the captured context into a function form and then binds it to a variable k. And then we can proceed to the evaluation of the body of the shift operator. So here we use k 2 times. So the answer becomes a 2 plus 1 plus 1 plus 3 and becomes 7. So other than shift and reset, there are many more variations like shift 0 and reset 0 and control and prompt, and then control 0 and prompt 0. So maybe you have noticed that all the delimiters are denoted by angle bracket, and they're all the same, just the name is different. And the capturers are different, shift and shift 0 and control 0. All these things are different. And there are also a type system for each of these operators, but not for all these four operators, not a type system for all that includes all the four operators. So when we back to the initial motivation, I wanted to compare the different kinds of control abstraction in a type level. But so it was clear that we needed a kind of a unified notation to understand these kind of four operators in one type system. So that is our main goal, to design a type system for four operators in a unified notation. And also we wanted to ensure that the type system maintains the same typability with previous studies. Okay, so far I talked about my motivation and the goal of my research, so I'm going to talk about how we design our type system. So, so first I'm going to compare shift and control shift 0 and control 0, and the difference is just the delimiters. So it is colored in red and blue here. So as you can see in the table, control does not have red delimiters, and then shift 0 does not have blue delimiter. And then control 0 does not have red or blue delimiters. So this difference might seem very subtle, but when we try to evaluate these operators, the result is very different. So what happens if we do not have red delimiters? So in this example, I use two control operators. So one of them is included in the captured context K1. And since, as I mentioned, control does not have delimiters in a red area, So control can capture the context outside K1 like this. So these kind of thing happens only when only in the case of control or control 0. So similarly, if we didn't have a blue delimiters, what happens? So in this example, I use two shift-0 operators in a nested way. And as I mentioned, since shift-0 does not have delimiters in blue area, shift-0 can capture context the outside of the outer context like this. So this kind of thing happens when in the case of shift-0 and control 0. Okay, so I just wanted to quick review of these two kinds of dynamic behaviors. So a control and control 0 can capture the context that invocate another one. And we are going to call these kind of contexts as trail of invocation context. And the name is just a little bit long, so I'm just going to call it trail. And also, shift-0 and control 0 can capture the outer context, and I'm going to call it meta continuations. And for these kind of trail and meta continuations, so these two can be changed dynamically during the execution. So we are going to track these trail and meta continuation even in type systems. So please keep in mind that these kind of two things, trail and meta continuation, will come up repeatedly in my presentation. So I put some hint at the bottom of the slide there, so you will notice. So I talked about the two kinds of dynamic behaviors, and they also appear in the CPS interpreter. So here is a interpretation rules for four operators: shift, control, shift-0, and control 0. And this CPS interpreter is based on a standard CPS interpreter. As you can see, it receives a environment variable as role and a continuation as kappa. And then we added two new variables to track context information. As you can see, the red one and the blue one, and a T is for trail, and M is for meta continuations. And how do we add some information to the trail to meta continuation? So for example, when you see a shift and shift-0, so they use meta continuation to track the context information. And also in the case of control and control 0, they use trail to track the context information. And if you see the shift-0 and control 0, you can see that these two operators have access to the inside of the meta continuation, so that so to do so, those meta continuation are expanded like kappa 0 and T0 and M0. So from that interpreter, we can derive the whole type system. So for example, in the case of control 0, we have a typing rule for it, as you can see. So as I said, control 0 can add the context information into trail. So we need to be a little bit careful when we add in the information onto trail. So we created additional typing constraints to check whether the type of new context and existing context are compatible with each other. So by adding these kind of typing constraints, we can say that if the type E is typed in our type system, the evaluation of E terminates. So this is because we implemented a typed interpreter on the prefix system Agda. Okay, so as for the derivation approach, so originally, Danvy and Filinski derived their type system for shift and reset from the corresponding CPS interpreter. And other two existing studies also follow the same approach. Similarly, we follow the same approach, and we derived a type system from the Shan's interpreter proposed in 2007. So this interpreter includes all the four operators, and from that we derived our type system for four operators and in a unified notation. And also we proved the relationship with existing systems. So let's look at that in the next slide. Okay, so here is a little bit complicated diagram here, but basically what I'm doing here is to I'm just doing a transformation in types. For example, when we try to transform the type of DF to 4D, by the way, DF stands for the type system by Danvy and Filinski, and 4D is our type system for four delimited control pairs. And we are doing various transformation. So DF didn't have the information about meta continuations, and also it doesn't have a information about trail, so we needed to perform a CPS transformation, and then we do some transformation to add trail information, and then we defunctionalize the type to get our 4D type. So similarly, we did the same thing for the CP. Type system CP stands for the control and prompt. So CP and for the control and prompt, they already had the trail information. So we just did some CPS transformation to add the meta continuations information. So similarly, the same thing can be said with the type system for shift 0 and reset 0. So from MB to 4D, we just added trail information because MB already had the information about meta continuation. Okay, to summarize, we designed a monomorphic type system with the four delimited control pairs in a unified notation. And we also proved the typability between the existing systems. So we think we are now ready to compare it with other control abstractions such as effect handlers as a future work. Okay, so that's it. Thanks for listening.
So questions? Thanks, very interesting. Have you thought about multi-prompts delimited control? Does that fit into the same kind of framework?
Yeah, that is one of the things. That is one of our future work to do. So yeah, I wanted to expand our type system to include a multi-prompt. Yeah. Yes.
And more generally, I mean, we seem to have this huge space of different control operators. I mean, there's these four, but they're quite nicely uniformed together. But there are many, many, many others.
Yes.
Do you think there's any hope of, I don't know, somehow understanding them all in terms of one type system?
Yeah, hopefully, but so as a next step, I'm just going to try out the effect handlers, deep and shallow handlers with the delimited continuation is our next goal. But I don't have any plan other than that. But yeah.
Great, thanks.
Thank you.
Thank you. Other questions? I have only one question. Well, so you gave a single type system for four different JVU control pairs.
Yes.
That is good. And the guiding principle for you is that to as explicit as possible. But then the resulting type system has a relatively complicated type.
Yes.
But also for outsiders, maybe also I'm not an expert, but for outsiders, I guess they want to know a single understanding of all these types. So if the guy is an ML programmer or designer, then maybe he doesn't need any kind of answer type polymorphism, but answer type modification, but he may need principal type, principal types and so on.
Yeah.
So can you give some kind of hint or some suggestion to design such a, to satisfy such a need?
Yeah. Yeah, as you said, it's our type system only has a kind of limited support for the principal types right now, but yeah, so I'm going to as you said in a previous question, I'm going to compare it in other control abstraction, and as well as I'm going to put some other types like recursion or polymorphism. Is it does that answer your question? Slightly?
Yeah, my question was very big, but it's not a criticism, but I think the resulting type system has a relatively complicated typing rules, and for outsiders, they may not need such very expressive type system. And then, what can you give to
maybe to make it more understandable, expressible for the users. Maybe we can make it a type. Yeah, making a type checker for that. Yeah, there is a huge space or many approaches to do that, but yeah. I haven't think about it. Haven't think about it in a very detail, but yeah, that is something we wanted to try out in the future. Yeah. Thank you.
Oh yes.
Yes, thanks for interesting talk. So in my memory, the type system for shifto 0 and resetto 0 supports some typing
Yes.
for embedding peer computation into in-peer computation.
Yes.
So my question is that your type system support such as typing?
No, currently no. So yeah, so I wanted to expand my system to support subtyping in a future work. Yeah, but yes.
So
currently no.
sorry. Do you think is it possible to support such a subtyping? Or
Might be.
Maybe. Yeah.
Might be. Yes.
Okay.
Any other questions? Okay. So I think it's time. So let's start the speaker again.
Thank you.